Last time, we started to map continuous fluid system to the Ising model and via so-called lattice gas model. And we wrote down the Hamiltonian for a fluid, which is a sum over the kinetic energy term and the potential energy term, and for m particles where n goes to infinity, and those particles can actually move freely in the fluid, and the potential term contains these two-body interactions and also the three-body interaction. So that's the lowest order contributions to the interactions among the particles. And you could imagine that you could add more terms in your Hamiltonian or in the potential term to describe four-body interaction and five-body and so on and so forth. But this is not necessary, and it is sufficient to actually consider up to two-body interaction. And the on-site potential term is described by the U1, and this ground canonical ensemble could be computed by this partition function, which is the trace of the e to the minus beta h minus mu times n, where mu is chemical potential. And capital N is the total number of particles. And as indicated previously, we could integrate over this kinetic energy term by a Gaussian integral. And then we get this lambda, this thermal wavelength vector, and e to the minus beta mu there, and all they get is power of n, and 1 over n factorial times this factor qn, where qn is the integral over this Boltzmann weight of this potential term. And the free energy of the system is defined by taking the logarithm kBt log of z with the minus sign of that partition function. So that's just the partition function for a fluid. Then we try to manipulate this fluid Hamiltonian to map this system onto a so-called lattice gas problem, where you could just mash this volume of your fluid into a equal partitioned little cell or little unit cube. Within each unit cell, there's only at most one particle occupied in that little cell, or there's no particle there. Okay, so this is called this hardcore condition. And this hardcore condition is an approximation to the fluid system, where you know that in the real fluid, all those molecules of a fluid can actually freely occupied in any space. So this hardcore condition is just approximation to the real fluid system. But this is a very good approximation, as we'll see later, that more or less the molecules in the fluids satisfy this hardcore condition, that we could partition this total volume of the fluid in terms of an equipartitioned unit cell. And within each unit cell, you could populate either 0 particle or 1 particle at most. And then we could rewrite this potential term in terms of the density of the particle, rho. And this density of particle is a bunch of delta function in real space and sum over all the sign indices. And you could approximately consider this occupation index Ni as the particle density rho in real space. So you could sort of change your variables from this position vector of each of particle or molecule inside the fluid in terms of a unit cell index I over the same volume. So the continuous variables of the fluid problem is mapped onto a discrete unit cell. It's kind of a lattice problem, but we know that this is not the crystal kind of a lattice, but so-called a lattice gas. So this is not the crystal structure of a solid, but a lattice of some kind of weakly interacting molecules or particles, so-called a lattice gas. It's a bunch of weakly interacting particles in the unit cell. So we could approximately consider that the fluid system as a lattice gas. But within that language of this occupation index Ni, we are able to rewrite this potential term of the fluid Hamiltonian in terms of this expansion of this Ni to linear order and to the quadratic order. So you can see that the U1 term is nothing but this chemical potential term, which multiplied the particle number will be some sort of a potential energy, which is more or less the same term as mu. And the U2 term is a two-body interaction, which is very clearly seen in this form because this Ni and J term multiplied by this U2 interaction strength tells us that this is some kind of a density-density interaction. It's like a Coulomb interaction of charged particles. Instead of a charged particles, density-density interaction, or the gravitational force. Okay, in other words, inside the fluid, the molecules and particles interact by some kind of a density-density interaction. This is the two-body interaction, which is the lowest non-trivial order of the interaction term. And the kinetic energy term is still the same because we already integrated out this kinetic energy part of the partition function. So we should only concerned about the potential energy term. So now we arrive at this lattice gas system where the potential term consists of one body on-site interaction and the two-body nearest neighbor interaction term. Okay, suppose that the I and J is just a nearest neighbor site like this. And this is the short-range interaction. We assume that the interaction between these two particles is finite only when they are in the nearest neighbor sites, and otherwise there's no interaction. So now we are in the position to map this lattice gas model to an Ising model. And this mapping is an exact mapping, as we'll see in just a moment. And we know that the first step is from the fluid to the lattice gas, we sort of take some approximations. So how are we going to achieve this goal that we map this lattice gas Hamiltonian to the Ising model of the spins? So let's just relate the lattice gas to the Ising spin with the following identifications. So suppose we define this occupation number as function of a site is one half of 1 plus SI, where SI is some kind of a effective spin, which takes minus 1 for n equals 0 and plus 1 for n equals to 1. So you can see that n, this little n, can take only two values, 0 or 1. It is two-level system, which means that this particle can take either zero occupation or a singular occupied configurations on each of unit cell. So it's kind of a two-level system. In quantum mechanics, this two-level system is very famous, so-called quantum two-level problem, which can be mapped onto this quantum dot problem. But here, this two-level system can be mapped onto the spin system because the spin, the simplest example of the spins is actually the spin 1/2 system, right? So you can have either a spin up or spin down states, but with the spin up, we have, say, plus 1/2 h bar as an angular momentum, spin angular momentum. Remember, this real spin of an electron takes just plus and minus half of h bar as a spin angular momentum. And likewise, here we consider effective spin or pseudo spin, for example, which takes only two possible values. One is plus 1, another is minus 1, depending on this occupation of particle. So you can very clearly see this. So when S is actually minus 1, you get 0. When S is plus 1, you get 1. So let me just map this to more explicitly. Okay, so this is the trick. You can map a two-level problem onto the spin 1/2 problem. Okay, and this mapping is exact. So now you could just change your variables from this occupation language to the pseudo-spin language. Okay, so you can rewrite your Hamiltonian, this two-body interaction, in terms of the spin-spin interaction times quarter 1 plus SI plus SJ plus SI dot SJ. Okay, so we are almost there. So let's take a short break. When we come back, we will continue deriving the Ising model from this lattice gas Hamiltonian. So just a moment ago, we arrived such a potential term in terms of the spin degrees of freedom or pseudo spin degrees of freedom by mapping the occupation variables onto a pseudospin, up or down, or plus or minus 1 degrees of freedom. And we can rewrite this potential piece of the Hamiltonian in terms of spin variables, Si or Sj, and the two-body interaction term in this language now becomes a constant term and plus a term which is linearly proportional to the spin, which is effectively Zeeman term under the magnetic field, and also the two-body interaction or the nearest neighbor spin-spin interaction, where the spins can only take up or down or plus or minus 1. And the third term is precisely the Ising term in the Ising model. But what about this chemical potential term, the U1 term, and also this minus mu and I term in the Hamiltonian? Well, you can see very clearly that this U1, this on-site potential, only shifts the chemical potential mu, and we can redefine the chemical potential mu by absorbing the U1 interaction strength, or we can simply just set U1 to be 0 for simplicity, and this is what we'll do. We simply just set U1 to be 0 because we know that U1 could be absorbed into this chemical potential by shifting a chemical potential. So we don't care about the U1 term. So now this lattice gas Hamiltonian, the potential term, now becomes a constant term E0 and the Zeeman term Si dot little hi, and the exchange term of the Ising coupling, and all this coupling constant or constant energies are defined here, where this capital E0 represents some kind of a chemical potential term in a Hamiltonian proportional to this total number of particles. And this little h is sum over this chemical potential and this U2 interaction strength, two-body interaction. This little z here represents the number of neighbors for each side on the lattice. And the Ising coupling J or minus J is given by this U2 divided by 4. So there is a one-to-one correspondence between lattice gas Hamiltonian and the Ising Hamiltonian. Okay? So remember that previously when we defined this Ising model, there are only two terms in Hamiltonian. First term is the spin-spin coupling with a ferromagnetic type, whereas J is positive, but there's a minus sign here. And this corresponds to this repulsive two-body interaction in the fluid. Suppose we have attraction between these molecules in the fluids, then this J flip the sign. There is an overall constant of energy E0 in this mapping, right? But this doesn't change phase transition, or it's just kind of an energy shift. So now let me just link this partition function of a lattice gas model to the Ising model. E to the minus beta E0 partition function of Ising, field, exchange coupling, and number of particles. So apart from this overall factor e to the minus beta E0, this partition function of a lattice gas is exactly the same as that for Ising model. Okay? But that constant energy E0 doesn't change physics or the phase diagram or the phase transition at all. It's just a constant energy shift. So after constant energy shift, these two models are equivalent. Okay? So we arrive rigorously the statement that the lattice gas model is the same or equivalent to the Ising model. Okay? So we finally arrive what we stated earlier. These two models are equivalent. Okay? But superficially, you cannot imagine that the liquid system is somehow linked to the Ising model. Of course, they are not exact mapping. As I mentioned, the approximation that we made coming from the fluid to the lattice gas tells us that the fluid system is not 100% equal to or equivalent to the Ising model, but up to some approximation. But this approximation is reasonably good enough for us to establish such a mapping. So remember, the approximation we made coming from the fluid to lattice gas is this hardcore condition, that you have a hardcore unit cells periodically arranged in a large volume of your fluid. And within each unit cell, you can populate up to just single molecule. Okay, so now let's look at the problem from the different perspective, meaning we could derive or arrive the same conclusion from a different perspective. So we could just directly sum over this configuration. We can perform a direct configuration sum in the partition function of a fluid. And then we make some approximations, and we could arrive the lattice gas. Okay? It's very similar to what we have been through, but let's just take this path to arrive the same conclusion. Okay, so remember this Qn, which contains the integral over this potential term with the Boltzmann weight, U2 RIRJ. So that's the potential part of the partition function that we defined earlier. And to achieve this derivation, we need some approximation, which is pretty much the same approximation that we used earlier, that we assume the hardcore condition. So for this volume in real space V, we can imagine that there are many unit cells of size A, such that the probability of finding more than one particle is negligible, namely very, very small. So which means that this probability of number of particles in the cell, which is greater than or equal to 2, is almost 0. So this is some kind of a hardcore condition. And we could, again, equal partition the volume into n such unit cell, and within each unit cell, there is at most one particle populated there. So we can choose the cell size A, which is less than or equal to some radius, which I call the sigma, where sigma is a hardcore radius. And the purpose of making such approximation is to simplify this calculation of a partition function of a fluid. Okay? So I've used up all this blackboard space, so probably we call it a day, and we will continue next time. So in the next lecture, we will sum over this configuration integral or sum in this partition function. So in this partition function, remember, there's an integral over this dr over this volume, and under such a hardcore cell, you could make such approximation that this is given by sum over the discretized cells, where this alpha is a label of cells, and total number of particles given by the volume divided by this little volume of a unit cell, number of cells. Okay, so that's about it for today, and we will continue next time to finish this alternative mapping by directly computing this partition function with the hardcore approximation, and we could arrive the same partition function that we derived earlier. So see you next time.